Hi, good afternoon. I'm Chris Van Meter from Sac State. I'm a grad student. And we're going to talk about graphene, creating hot carrier cells for photovoltaics. So let's just dive right in. Here's a quick outline, a brief history of PV. I'm assuming maybe you don't know anything about photovoltaics. Maybe you do. I'm going to go to a quick background of what it is, talk about organic PV, and then keep that separate from graphene, and then talk separately about graphene, how it's derived, and talk about strength, and then a little bit about the manufacturing and mobility of graphene. And then I'm going to try to merge them together. So talk about graphene and PV together, how it's used, talk about hot carriers, and specifically what the article is talking about hot carriers and graphene. Close with a conclusion and references. All right, so here we go. So what is PV? So PV is photovoltaics. Generally with silicon, you have a PN junction, just like what you do in most solar application or silicon applications. Here's a monosilicon wafer. So what does that mean? It's a single cut or sliced crystal, ingot a crystal, and you can see it here on the corners, kind of rounded. So what they do is they just cut the flat edges, or they cut these edges off right here, and they make it more into a square, and that's more really for manufacturing of a solar panel. A cheaper way to make it is actually to quickly cool the silicon. So over here, it takes a long time to cool the silicon. It's very labor intensive, it's expensive. A cheaper way to make it, a cheaper panel, is just to let it cool really fast. The only problem is you get all these little crystals in there. Uh, that's not a bad thing, except for you just lose a little bit of efficiency. And we talk about efficiencies. For every square meter of the sun, you look up here, is 1,050 watts per square meter on the Earth. So no clouds, no haze, whatever. You should be getting about 1,050 watts of energy per square meter. Well, monosilicon crystals can convert about 25 to 26% of the power coming from the sun into electrical energy, where polysilicon can only do maybe 19, 20%. So you lose some efficiencies on that because of the breaks up into little silicon crystals. Thin film is the next one. So these are kind of your bendy, flexible things you're starting to see on backpacks and cell phone chargers. And they're breaking up in kind of four areas. Most of the thin film stuff, about 50% of it, is cadmium telluride. Telluride is kind of like a rare earth metal, like I don't know, platinum or something. The problem with cadmium is cadmium's toxic to humans. So what do you do with this stuff after you want to recycle it, right? And silicon PV up here, this lasts for 50, 60, 70 years. You lose about 1% of your efficiency per year. These thin films only last about 15, 20 years. So what do you do, right? So how do you get rid of this cadmium stuff? They don't really know yet. So even though it makes up about 50% of the market right now, they don't know how they're going to deal with it later. Amorphous silicon, I mean, you can think of silicon, you see C silicon for crystalline silicon up here and A silicon for amorphous silicon. It is it's a amalgamized silicon that's in like a substrate. Uh, Not bad. It's a little bit less efficient than a standard silicon wafer, but it's better than having toxic cadmium, right? So not as widely produced, not as much used as cadmium, but it's still available. This stuff, SIGs, copper, indium, gallium, selenide, is awesome. I mean, this stuff worked for the Cylinder Corporation. If you ever get a chance before they went out of business in 2011, this is what they were using in tubes. Amazingly efficient, up in the 26, 27 percent range for efficiencies. They're putting on roofs. They're super light. They were in tubes. The wind blows right through them. The problem is nobody's making them anymore. And then you have these gallium arsenide. So these are the four thin films. Gallium arsenide is really expensive. The only application you see with this is for like space application. The great thing is it has about 28.8% efficient, which is really high, but again, it's really expensive. Down here in this figure, you have kind of a basic explanation of how solar works. So you have a photon that comes in. You have a typical p-n junction with a depletion zone. And this photon, it just excites an atom up into the conduction band. Luckily enough, there's enough of electric field in here so that electron gets shot through and creates some current. And that's how we use solar PV. I'm going to give a shout out. This Grid Alternatives down here is a nonprofit solar installer. I'm a high school teacher, and we've put our students through about 50 solar installations. This gives you some volunteering hours if you ever want to learn more about solar for residential. Hey, give it a try. So that's my plug. All right, so there's a third type of PV out there now. It's called organic PV, and it's more of a like a plasticky PV. It's not as widely used, and it's not very efficient. It breaks down pretty fast. I mean, the other ones we were talking about decades. This one, 10,000 hours, less than 10,000 hours. This is like a year. If these 8 hours a day, these things break down in 6 months to a year. They're no longer any good. And I think they said in the first month they were breaking down anywhere from 10 to 30%. These are really reusable, cheap, throwaway plastics, solar. This is how they work. There's three areas: single layer, bilayer, and bulk heterojunction. Single layer, these words are really interesting: LUMO, HOMO, and excitons. LUMO just means conduction band. HOMO means the valence band. Excitons just mean electron hole pair. They're inefficient. And when I mean inefficient, like less than 5% efficiency, but they can be massively produced, quickly, cheaply, massively produced. So if you want like a dirt cheap, really quick solar, you can get it from here. The really interesting thing, and I got to put this out, when you go online, you bring stuff down. These are all upside down. So actually, the sun for these comes through this ITO, indium tin oxide, up from the bottom. I mean, obviously, we don't have sun coming up from the bottom, but this is the way it was presented on most of the pictures. So if you think about that, the sun's coming from this direction. These electrodes up here are just basic metals, and then in the middle is what we're talking about between the single layer, bilayer, and heterojunction. So single layer is you just have a bunch of p-type material, n-type materials all mixed together. The only problem with that is when the photons come in and kick off an electron, of every 5 electron hole pairs, you lose about 4 of them back to recombination. So that's why you get such inefficiencies. A little bit better efficient is to actually separate the donor material and acceptor material. And what you can do then is you can set up a little electric field, and you get efficiencies in close to 10%. So this is much better, obviously, because you don't have it just swimming around together. You can actually collect a lot of those electrons. You still have the ITO, which is a mostly transparent substance right down here. It just kind of goes right through it, and gets into this PN junction. And then that brings up the third one, which is a bulk heterojunction. So the really cool thing is it's like a combination between these two. Bulk heterojunction has about the same efficiency, and I mean about almost the same efficiency as these kind of like bilayer PN junction, but it's done more like this single layer. And this is how it works. If you look in here, you can kind of see the blue and the green is kind of separated a little bit. It's because you have big chunk areas of P material and big chunk areas of N material. And it leaves enough to create enough of electric field for the electrons to get kicked out and the holes to get kicked out, as the photon comes in and provides energy to the electron to kick it up in the conduction band. But still has the same efficiency as this, but hey, this is actually really, really cheap to make. It's much easier to make and produce than this bilayer stuff. So that's what we're moving into. They have like 4-layer heterojunction stuff now that's even more efficient. They're getting better and better with these organics, but again, they're still, I mean, efficiency is great, but they still don't last very long. They break down pretty fast. For National Renewable Energies Lab, they have this diagram here. You can see the ITO here in the orange layer. I thought this was just really cool because you can kind of see that this absorber material is kind of like that single layer, bilayer material. But the reason I brought this up is because graphene is really the first time we start seeing graphene. And we're going to talk about graphene in a second, but we need a substance that's nearly transparent to be able to allow the sun to come in, but still allow electrons to move. And so we're going to replace this ITO stuff with graphene. So that's the next slide. So what is graphene? Graphene is a thin layer of pure carbon. It's two-dimensional, and you can actually make this at home. You take some graphite and you put it on a piece of Scotch tape, and you take another piece of Scotch tape and smash it all together between the two pieces, and you start pulling the Scotch tape together. And you can do that time after time after time, and you get down to this single layer graphene. In fact, this is one of the ways that actually we're able to do this in the lab. Crazy. It's called the Scotch tape method. And the cool thing about this is when you get graphene down to this hexagonal structure, one, it's pretty transparent. It blocks less than 3% of the light. And two, huge mobility. It allows electron to move really freely through this carbon graphene. And then the next thing is strength. And I'm talking about mobility in just a second. I want you to see that. But strength-wise, this is unbelievably strong. It's one of the most strong substances we can see. It has a 42 Newton per meter of tensile strength. And the equivalence, if you take a piece of saran wrap and you take a pencil on it and you put a car on top of, like a 2,000-pound car on top of it, that's where it would break. I mean, it has that much tensile strength that it can hold that much force on top of it. It's pretty absolutely amazing. I found a website that was trying to describe it, but it's absolutely amazing for tensile strength. So how do we make it? So manufacturing, if you're not going to sit there and pull tape apart, there are larger ways. This is a conceptual diagram of how you can to make this and mass produce this. So they take a piece of copper foil, they run it through an etchant as they're squeezing on the polymer support with the graphene. And then you remove the copper, you're left with graphene on a polymer, and then you deposit the graphene from the polymer onto a target, right? That's kind of a way to manufacture it. But let's look down here for mobilities. We were talking about how cool this stuff is, but look at this mobility, greater than 200,000 centimeters squared per volt second. Now, to give you perspective, you should see mobilities like this from silicon in the 2 to 3,000 range. So imagine this is 200,000. Mobility is the ability for an electron to move, right? So now you're talking about a silicon is 2 to 3,000. I mean, this is 100 times faster. It's 100 times more than silicon. Over here, you see this diagram right here. This shows the blue line is just intrinsic graphene. The red line is they've annealed it. They did a current annealing at 600 degrees Celsius, and they were able to find the graphene itself, and this is where you get some better peaks. So then the red here is the copper anneal. Look how high that gets for mobility. Unbelievable mobilities. And hey, since high mobility, you lose the resistance on this, 35% less resistance than copper, 1 microohm per centimeter. That's amazing, right? So it's strong, high mobility, and you can see right through it, right? So we talked about PV, we talked about graphene. Let's move into how do we merge them together. So hot carriers. When we've been talking about hot carriers in the classroom, we've been talking about one of three things. I think the Johnson Martin book had a pretty good way of describing. This is not the figure from the Johnson Martin book. I can't find it, but it gives the example. So one. Hot carriers they're high velocity carriers, right? They're more than the normal thermal velocity. And impact ionization avalanche, they punch through. They allow the carriers to punch through. The problem is, first, between the drain and the bulk, if these start punching through, then you're setting up a voltage potential between the drain and the bulk, which can set up some latch-up problems, right? Second, if you have some carriers punching through the oxide and going up in the gate, you can have some problems with your threshold voltage. And lastly, things that we've talked about in the classroom, what if you have punch between, impact ionization between the source and the drain? Then you no longer have an effective channel, an L, right? You're just kind of blowing right by it, and now you don't have a switch anymore. You just have something that's just going to let unlimited current flow, mostly unlimited current flow through. That's not really what we want. Well, I want you to take a look at that. That's not what we're talking about when we're talking about hot carriers. Hot carriers, when we're talking about semiconductors, that's what we're talking about. Some problems with it. But hot carriers in graphene is a little bit different. That's the ability to take a photon and kick up electrons into its conduction band, and push it up. That higher more than the thermal velocity. This impact ionization is actually kicking that electron up. What they've been finding is under high energy photons, this is called electron multiplication, because actually what they're doing is they're kicking up more than one electron with one photon. So one photon is going in and kicking up a bunch of electrons. But this high energy photon in the violet range produces even more electrons than maybe in the lower energies in the infrared band. So they can take a broad spectrum and they can kick up a whole bunch of electrons. And they've been doing this with two types of substances. The first one is with epitaxial. This is really the heart and the meat of the article. Epitaxial graphene. So this is a deposited graphene on top of silicon. This is something that would be good for semiconductors. And it leaves 1 to 2 layers of graphene on top of silicon. We're going to talk about mobilities in a second, and diffusion diffusion coefficients. And then the other one is a reduced graphene oxide. This is cheap to make and really easy to make. And this is just what did they say? This is just fabricated by spin coating graphene oxide flakes on a quartz substrate. So really cheap and easy to make. A lot harder to make with like chemical vaporization, vapor deposition, right? CVD. But the one cool thing over here is what they found is this epitaxial layer in the blue is only about twice as much mobility as this reduced graphene oxide. So this stuff is so good that even when we make it cheaply, we only have about half of the mobility that we normally had. And look at this mobility. You're still 30,000 centimeters squared per volt second. That's huge. That's huge. That's incredible mobility for even a cheaply made graphene particle. And the way they did this is I think they shot a sapphire laser at it at 810 nanometers, and they were measuring the effects of it off of it. So just super cool stuff. So we were talking about photovoltaics, silicon crystal, asilicon, C-silicon, thin film efficiencies. We talked about graphene, mobilities, the strength, and how thin it is. And then we talked about hot carriers and graphene through CMOS and diffusion, mobility, and graphene. So have some references for you. Take a look at the references if you want, quite a bit there. And that's the end of my video. Thanks for watching.